Okay, so welcome to the introduction to the second sprint. I would like to start with a short retrospective of your results in the previous sprint and your results also of the survey. So according to the survey and also according to our impression when meeting you, the majority of the students will learn well during the sprint. They understood the material, they managed their time well, and they did well on the homework. At the same time, about even more than half of the students didn't like Scrum. They said that it's taking too much time. And the conclusion that we understand, we still need to pass the results, which is just a very partial impression, is that Scrum is working well, but is unpopular. And why do we think that Scrum is working well? Because in previous years, students didn't perform so well in the first sprint or in the second also. And it's either because you are smarter than previous years or because Scrum is working well in our opinion. And we will let you choose the right answer here. So you didn't like Scrum, but you didn't suggest alternatives to Scrum except traditional lecture and just trusting you to meet in teams and do everything perfectly, which we cannot do. So what I'm going to suggest some version of Scrum. So those of you who worked well in Scrum are encouraged to continue. Those of you who would like to change Scrum, for the next sprint, I'm going to present at the end of this introduction some variation that you can use. What about traditional lectures? Well, I think that some of you said they prefer 240 minutes of remote non-interactive lecture, which is very similar anyway than the videos that you get right now from us. Because it's non-interactive, we don't think that it's the right solution. We think that the 90 minutes of interactive sessions every 2 weeks that you get right now is much better. And in fact, few of the teams use the whole 90 minutes. So we don't think that you are lacking interactive sessions with the teaching team. So if you really think you need more time with the teaching team, you can always contact us or use the whole 90 minutes that you get. Also, it allows us to evaluate you every 2 weeks, which you won't get in a traditional lecture. Okay, so we covered proof techniques. We are moving now to the next topic, proof technique called induction. Let's have a look first on another related topic, which is called the well-ordering principle. When we try to prove that square root of 2 is irrational, if you remember, we said we proceed via a proof by contradiction. We assume square root of 2 is rational and reach a contradiction. How do we reach a contradiction? Because it's rational. We know that exists, and we're going to see the symbols in the next sprint. M and N, which are natural numbers, so non-negative integers, such that square root of 2 is equal to M divided by N, because it's rational. And in addition, M is minimal. Okay? This is another assumption. We're going to come back to it at the end. So if square root, if this is true, then we can just develop it a bit to m squared divided by n squared, which means that 2n squared equal to m squared, which means that m squared is even, which means, using some lemma, that m is even, which means that there is k, natural number, again, non-negative integer, such that m is equal to 2k. And if we plug it in, we get 2n squared is equal to k squared, which is equal 4k squared, which means that n squared is equal to 2k squared, which means, again, that n squared is even, using the same lemma before, n is even, which means that exists L natural number such that n equal to L. Okay, so this is what happens if square root is rational, which means the square root of 2 is equal to k divided by 2L. And this is in contradiction to the assumption that 2k is minimal, because we find now another number which can represent the upper part of the fraction for square root of 2, which is k. K is smaller than 2k, right? And it also can denote, using L, the rationality of square root. Okay, so this was the proof, and what's the problem with this proof? How do we know that there is? How can we choose a minimal m? How do we know that it exists? How do we know how we can find it? Okay, so this question is solved by, in addition, we can say axiom. Every non-empty set of non-negative integers has a smallest element. Okay, and how do we fix the proof of square root of 2? Well, we say if it's rational, then it's equal to some number. But let's assume that it equals to many. There are many different possibilities, right? Not only one. We know that there is at least one, right? Because our assumption is that a square root is rational, so there is at least one. But we assume that there are many. And now we take all these numbers. Might be infinitely many, but at least it's not empty. And all of them are non-negative integers. And we know that there is a smallest element here. We don't know which one, but we know that there is and that we can choose it. Okay, this is what the well-ordering principle says. So we can say in the previous part, we know we can choose that m is minimal because by the well-ordering principle. Okay, because all the m's, all the possibilities form a non-empty set of non-negative integers, and therefore we can choose a minimal one. Okay, so this is something that you are going to read and you are going to use in proofs, etc. Now let's move to the main topic of the sprint, proof by induction. A proof by induction tries to solve a certain thing. Here we want to prove that for every positive integer n, then this equation holds. The sum of the numbers until n is equal to n plus 1 divided by 2. Okay, this is what we want to prove. This means that, and first of all, in order to prove by induction, you need first of all to be able to denote it in a formal way, using a predicate. So we can say this statement is equivalent to Pn is equivalent to 1 plus until n is equal n times 1 divided by 2. Okay, this is a predicate. We learn it again in the next sprint, and this means just some statement which is either true or false. So we claim that this is either true or false, and we denote it by Pn. We just give it a name, which is parameterized over n. So now what do we want to prove in this theorem? We want to prove that for every n which is an integer, n is bigger than 0, P1 holds, P2 holds, P3 holds, until infinity. Okay, we want to prove it for infinitely many n numbers. So how can we prove it? We didn't see yet a way to prove something for infinitely many possibilities, except sometimes by proof by contradiction. So how can we proceed here? We can use induction. Induction says the following. If you can prove it to the base case, this is the base case. In our case, the base case is P1, sometimes it can be P0, but this is the minimal element in your set. And you can prove it, you can prove the induction step, which means that if you prove it for some arbitrary number k, then you can, if you assume that it's true for some arbitrary number k, you can prove it for the number k plus 1. If you do these two steps, then you know that it's true for all the possible numbers, all values of n. And how can it be? Because we started with the minimal element, and we proved that if one element is true, the next element is true, then automatically we also proved it for P2, right? Because you can assume that Pk now is 1, k is 1, and then k plus 1 is 2. So we know already that it's true for 1, right? So this can be replaced to P1 implies P2, P2 implies P3, etc. And because you know that it's true for P1, you can apply the chain infinitely many times. So this is how you can prove something for infinitely many values using induction. So how do we use induction in practice? Okay, let's have a look on this example here. So we start the proof with the note. We prove, we prove for every n natural number bigger than 0, Pn holds. Okay, this is how we start the proof. First of all, you define what is Pn, of course, and then you say, okay, for the base case, we need to prove that P1 holds. So let's try to prove it. 1 times until 1, right? N is equal 1 is equal 1 times 1 plus 1 divided by 2, which is equal 1. Perfect. We proved it for the base case. So normally the base case is relatively easy. The induction step is the harder part. Induction step. Prove it for pk, assume pk and prove it for pk plus 1. So how can we proceed? First of all, let's write the assumption. Okay, so we assume 1 plus all the numbers until k equal k times k plus 1 divided by 2. And we need to prove. Okay, and here you can choose which method you want, by contradiction, by cases, any one of your preferred proof methods. 1 plus k plus k plus 1 equal k plus 1 times k plus 2 divided by 2. Okay, so now you have a normal proof. And here we are going to proceed by a direct proof. Okay, so we need to prove that. So what does it mean? We have this. So the first thing I want to do, and we have this assumption, and we need to use the assumption as we know. So we can either start from the assumption and try to get to the conclusion, or we can try to reduce the conclusion and see that you can apply the assumption. So let's do the second thing, okay? So I just going to remove k plus 1 from both sides of the equation and see what happens. So 1 plus all the numbers until k is equal k plus 1 times k plus 2 divided by 2 minus k plus 1, right? And this is equal k plus 1 times k plus 2 minus 2k plus 1 divided by 2. And this is equal to k plus 1 times k plus k plus 1 times 2 minus 2k plus 1 divided by 2. And this is equal to k plus 1 divided by 2. Okay, so what did we get? We get 1 plus k. So we manipulated what we want to prove, and we got 1 plus k equal k plus 1, and this is our assumption, right? So we use and you can also call it by the induction hypothesis. By the induction hypothesis, we know that this is exactly equal to pk. We know that pk holds, and therefore we finish the proof. Okay, so this is an example of a proof by induction. This is the main topic, and you will do lots of proof by inductions during this sprint. So to summarize and to explain a bit how is sprint 2 going to happen. So it's 2 weeks, exactly as sprint 1. You are going to learn induction and the well ordering principle, and in addition you are going to learn a typesetting language called LaTeX. LaTeX is a language which allows you to write using a normal keyboard, complex mathematical formulae, and we are expected to use LaTeX in order to write the homework, and all the information is on Moodle. You will again have access to expert meetings, but in this time you will not use the expert meeting request form, but you will actually be assigned automatically either the first Wednesday or the first Thursday, 60 minutes to have the expert meetings. So you are going to start, today's Friday, I guess you are going to start on Monday. You will have Monday and Tuesday in order to already come up with the questions. And then on the second week, you have an optional again 30 minutes on Wednesday. So how are you going to use Scrum this sprint? Again, I mentioned those of you who worked well in the Scrum method are encouraged to keep using that. You already know it, you already understand how it works, and it works well because you really did well this sprint. Those of you who are really want to change Scrum, we are suggesting having a variant of Scrum. We'll try this sprint. If it works, you will be able to continue using that. If it doesn't work, we'll come back to Scrum, or you might always suggest alternatives which ensure that you manage both your time and your team in a proper way. So what is the variant? The variant is the following. You do your sprint planning meeting. You do the sprint planning meeting, but you don't give estimates. Instead of that, you are going to explain what you are going to do on Monday, on Tuesday, on Wednesday, and every day until the oral exam, not including the oral exam. You don't need to assign any task there. Okay, so you need to write exactly what are the tasks each member of the team is going to do for every day. And you're going to hold, and the Scrum meetings, also for those following Scrum, we agree for relaxing this standing meeting for every day, and you can do it every second day. So stand meeting max every 2 days. Okay, and then you need to write minutes as before, as in the Scrum, and explain which team members were presented and which task you finished in the last 2 days that you were supposed to fix. Okay, so we expect a report as detailed as the Scrum report that you submitted for the first sprint, also for this other method. And if it works well, then you don't need to do estimations, you don't need to manage the Trello board, but you need to do this planning at the beginning. Okay, we are going to evaluate it again at the end of the sprint, and you are supposed again to submit all the information. So thank you very much. You can check now Moodle Sprint 2 for all the information, and I will see you on Wednesday and Thursday. Good luck.